everyone. In this presentation, we're going to look at techniques from artificial intelligence and applying those to better understanding our curriculum design. To begin with, let's define the curriculum. And the way I think most of us think of a curriculum is that it's simply the sequence of courses that are arranged into semesters. So in other words, in any given semester, what are the courses taken there, and what's the sequence of those semesters? More conceptually, we can look at how the ideas in an academic program are scaffolded, and we typically administer that through the prerequisites and co-requisites. So we could regard those as important parts of the curriculum as well. On the other hand, in the literature you'll find there are as many as 7 definitions of the curriculum concept, and some of those major ones include that there is an experienced curriculum, which is the curriculum that students see and believe in. So for instance, a student might say that, well, although the curriculum says we are supposed to be passing this course in that particular year, actually I know that most people only pass this course in this year. There's an operational curriculum, which is the way that the people teaching in the curriculum believe that it operates. And then there's the designed curriculum. So on paper, this is the curriculum that we believe students should be following. So in this work, we are looking at data mining the student records to understand the types of curriculum that we have and how intercorrelated the courses in those curricula are. And this is a screenshot from the system that we're using, which is called the Autoscholar Advisor. So the system hooks directly into the university's database, and when you select a faculty or a school, it brings up the list of academic programs in that faculty. So if we look into the chemical engineering undergraduate program, we can look at some of the previous work we've done in trying to predict student success or student progression. And in that work, we were trying to identify the main fail points in that academic program. So we had noted that every student was on the minimum time trajectory up to some point, and we were trying to determine what was the first point at which a student would fail off that trajectory into a longer time trajectory. So we realized as part of that work that in sorting all that student information, we were actually able to deduce what the curriculum structure was. And because we are deducing it from the student records, that is in effect the experienced curriculum, or the curriculum that's the student feels is applicable to their progression. So the way that we did that was we were able to sort in any given semester. We were able to sort the courses that were passed in terms of frequency and in terms of credits that the students undertook. And we found that when we did that, we were able to determine what the curriculum was to about 90% accuracy. And of course, the initial thinking was, well, then let's write a nice curriculum editor, and we'll catch that last 10%, and we'll have the perfect curriculum. On the other hand, being aware of these different definitions for curriculum, we realized, well, if we are determining this curriculum from the student data, then that is actually this experienced curriculum. So the advantage in our case is that we are able to quantify the difference between an experienced curriculum and the designed for curriculum. And if we have these curriculum objects, then it becomes possible to do all kinds of additional analysis and planning. And well, we'll look at some of that just now. But this is a screenshot showing the prediction of a curriculum, and highlighted in white are the courses that the Autoscholar program has correctly predicted, and then highlighted in this yellow color are courses where it's got it wrong. And if you look at this, Thermodynamics 1, Thermodynamics 2, and then some 4th year courses here. So if you look at these 4 errors in this prediction, and try to examine the reason for incorrectly predicting this course, you'll find that the system is predicting this course should be in the third year, first semester, whereas it actually occurs in the second year, second semester. And the reason for this is that there was this extreme high failure rate in this course. So because this course had such a high fail rate, the majority of students were only passing in the third year. So that's why that shows up in the wrong place here. And if you look at the reason for this course being in the wrong place, it's because this course serves as the prerequisite to Thermodynamics 2. So because the majority of students were only finishing Thermodynamics 1 in the third year, this course could only be taken in the fourth year. And so that's why so many students were doing that, and that's why the system predicted it incorrectly. And also, because this course is a prerequisite to the lab or industry project and the design projects, then these courses could only be taken later as well. So you see these 4 errors are really just one error, which highlights to us that this Thermodynamics 1 course is inhibiting the progression by our students quite significantly. So you see, analyzing the differences among these curricula can reveal important information for action in a curriculum. So this is our previous work. We wish to go further than that in this in the present presentation. But looking at what you can do once you have the curriculum object, you can auto-generate advice to students. So for instance here, this system is providing advice to a student. So this is his the credits he's accumulated over these semesters. And it's giving various comments here like, you've passed everything, well done, or here you need to, you haven't done as well now, and you need to pass at least 50 credits to get back in the green. Here, although you've gotten back in the green, you must keep working hard and you must pass at least that number of courses and so on. So you can dispense this kind of broad advice. And then also you can map a student against the curriculum. So you can see at a glance where the student is in terms of his progression. So here you can see at a glance that the student is sort of somewhere in the last quarter of study, and this is a person that needs to be supported to complete. So that's the kind of simple advice you can create. You can also give more sophisticated advice, so you can data mine that information and determine how much extra time the student has taken to complete. So the system can say quite judgmental things to the student. So for instance, your study is subsidized by the government. By taking this extra time to complete, you've cost the state and the university an extra so many rand. That's the South African currency. So that's also an estimated loss of earnings to you of this amount, and so on. So you can give that kind of advice to students. And we do find students respond to this type of advice quite seriously. They seem to be quite sensitive to this, to these reports. So even though our academics might be telling students these things, they seem to take it much more seriously when it's this kind of impersonal system that's dispensing it to them. And so maybe it's because they feel it's more unbiased. We don't quite know, but the observation is that students take this kind of advice quite seriously. So what we want to do in this presentation is actually look at, can we predict what a student is likely to do if we have the curriculum object and we've got data to fit to that. So can we develop a predictive model? And besides the student records, there is other data available. So there is bio data and so on available. So let's look at some of the processing that we can do towards that. So before we do, actually let's just define this Pearson R coefficient. So if we were to take a student's records, let's say in course 1, and plot those against the records in course 2, so each point here might represent, each point here will represent a student. So if we have a perfect correlation that the mark in one course correlates perfectly with the mark in another course, then we would get an R coefficient value of 1. If we perform negatively, if doing well on one course meant you did inversely well on the other course, you'll get an R coefficient of -1. Oops. If you have a result that has more scatter in it, but there is still some reasonable amount of correlation, you'll get an R value that's close to 1, but less than that. And if it's a complete scatter, then the R value goes close to 0. So that's the Pearson R coefficient. And we performed that kind of cross-correlation against a number of courses in the curriculum. So here we're showing the first-year courses, and we are cross-correlating those against the second-year courses. And highlighted in this yellowish color are moderate to good correlation values. So if it's not highlighted, there isn't a good correlation. And we can see here there are some surprising results. So the physics course, the first-year physics course, is fairly high and consistently high when it correlated against the second-year courses. So it's possibly the case that the physics course is serving an important scaffolding role in this curriculum. And that's important to know, because physics is actually often thought of as the course that should be dropped from the curriculum. So with many educational theorists questioning, why are our chemical engineers spending so much time on Einstein's theory of relativity? This is some data to tell us that, well, don't be so quick to cut that physics course out of the curriculum. On the other hand, if you look at this course, which is supposed to be an introduction to chemical engineering, you can see that's not preparing anyone for anything. The correlation values are very low, and if we accept a correlation value as indicating the degree to which a course is scaffolding, this course is not scaffolding much, and so that indicates to us there's some work to be done before this course serves in the role that it's intended for. So we can cross-correlate courses, and we can get some sense for how interconnected our courses are in the curriculum. And once we have that, we have then some kind of nominal target set. So we get some sense for what courses should affect what other courses. So for instance, here's a data set where we are trying to predict the result in Reactors 3. So we are trying to predict whether a student will pass or fail this course. And we are doing that by comparing with the results in Reactors 2, Maths, Economics, Psychology, and so on. And so this data set was selected to test out the algorithm, and the values are chosen, so it's deliberately difficult to fit this. So this mixture of passes and fails doesn't correlate easily to any other mixture of passes and fails in here. And the algorithm that we are using to try and fit this is, in machine learning, it's a general area of classification, and it's an identification tree that we are trying to generate here. So if we run that through the algorithm, the AutoScholar Advisor returns for us this kind of result, which we can interpret graphically this way. So according to that result, it's telling us, just ignore economics and psychology. They don't seem to play a role in the Reactors 3, in predicting Reactors 3 result. Whereas we should be looking at Reactors 2 results. And if you get marks in this low range, 0 to 40%, you will likely fail that course. If you get marks, sorry about that. If you get marks in this high range, you will likely pass Reactors 3. And if you get marks in this middling range, it's not enough to look at just Reactors 2. You also need to look at the Maths 1 result. And in that case, if you've passed Maths 1 the first time, you'll likely pass, and if you fail the first time, you likely fail. So this is a logic package. This is basically a model that tells us how to predict the outcome for Reactors 3. It's also something that we can use in terms of thinking about our pre- and co-requisites. So this tells us definitely Reactors 2 and Maths should be prerequisites for the course, but not so much these ones. That is if we are thinking about just the conceptual scaffolding. So this can help us, identification trees can help us to think about such things. But as mentioned, this is data that was pre-selected to test the algorithm. Let's try with some real data now. So let's do the identification tree setup here. And so we are trying to predict ENCH4RT, which is the fourth year reactors course. And when we run that against the data in the system, we find that it tells us the most important course to consider is 3RT, and that makes a kind of conceptual sense to us. 3RT is the preparatory material for 4RT, and we can actually capture 47% of the data using the symbols in 3RT. So if we look at the results here, it's saying if you get an A or a B in 3RT, you will likely pass 4RT, and you capture about 47% of all the data that was provided. Then it says, well, if you don't have an A or a B, then you need to start looking at 3MT. So this is the mass transfer course, and if you know chemical engineering, that course it's conceptually quite close to 3RT. That's probably second in terms of where it should be in terms of how closely it relates to 4RT. So this seems to be in the right place. And if you look there, it can capture 12% of the data using these categories. So if you don't have an A or a B here, but if you have at least a B, then you'll likely pass this course. So 3MT is a useful course to look at after 3RT. And yeah, so if you have an A or a B, you'll likely pass. Now here you see there's an F1, so that's a fail in the first category. So that means a result somewhere between 40 and 50%. You would likely want to discard this classification because likely it just happened that in the data set this is, but it doesn't quite make sense to us, so we would probably omit this. And then if you don't have symbols, if you don't have an A or a B for 3MT, then you need to start looking at 3PO, which is process modeling and optimization. So that is another major course which does fit well in terms of 4RT. So all this makes sense so far. And it's saying here, if you've got an A on this course, you likely pass. If you failed it badly, you will likely fail. But it only captures about 5% more of the data. So you can see the cumulative percent building up here. And so you can go through this list, and it tells you basically how to construct the logic or how to predict the outcome for 4RT. And if you draw that out graphically, you could represent it this way. So you first consider 3RT, and if you've got a high mark, you'll likely pass, and if you don't, then it's not enough. We can't clearly say that you'll fail, but you should then look at this next course. And so in this situation, if you have a high mark for this other course, then you'll likely pass. Otherwise, you also need to look at this course, and so on. So this is the identification tree for predicting 4RT. And so this fits, let's go back, this fits 72% of the data. So it can predict a student to about 72% accuracy. So in summary, there is a wealth of information in student records, and it can be used to analyze the curriculum and understand how interrelated the courses are. We have this AutoScholar Advisor, which is a framework where we can combine our analytical tools with data access and develop these kinds of conclusions. We are opening this to other institutions, so if you are interested in this, please contact me. And so we can quantify the differences between the designed for and the experienced curriculum. We can use the Pearson R coefficient to determine how intercorrelated the courses are. And we can try and predict outcomes in courses using identification trees. So the applications for that, it's not necessarily for predicting, and we don't quite know what to say to students. If we are able to predict that someone's going to fail, do you commit to a self-fulfilling prophecy and tell them that? What do you really do with that information? So we're not completely sure what to do in terms of generating student advice based on that. But what we can do is examine the support structures, and if we do know a certain course plays a strong role in the likelihood of passing or failing, then definitely it should be requisited that way. We can also look at other support structures if we can identify a student is at risk. And of course, we still have to examine how predictive this is. So we might want to cut out some of those branches on the trees to ensure that we get good predictive capacity. Thank you very much for your attention.